Welcome viewers. In this video we will see the dielectric boundary conditions. There are two boundary conditions available. We will see one by one. What is meant by dielectric boundary? There are two dielectrics are combined together. The line joining these two dielectrics nothing but a boundary. So what happen in this boundary? So when the flux line flowing through a single medium, they are continuous. So for example, if the flux is flowing through a single medium, single dielectric means it will be continuous. There is no disturbance. When they flow through a boundary formed by two different types of dielectric, they got refracted. Suppose if the flux line is flowing from one dielectric material to another dielectric material, there may be a chances of reflection both in magnitude as well as angle. So this can be studied by using boundary condition. So that we are going to, whether there is any change in the flow of flux in magnitude and angle, that we are going to study in this boundary condition. So the surface of glass board, one glass board is available. So this glass board and air is a glass air boundary, because air is also one of the dielectric material. It is available everywhere. So if we consider the glass board, on the surface of the glass board is one boundary. Over that air is available, that is another boundary, that is another dielectric. So the surface of this glass board is a glass air boundary. Now we'll see this boundary condition. First boundary condition. So when the flux lines flowing from one dielectric to another dielectric, what will happen if there is any change in the flux both in magnitude and angle, that we are going to study in this boundary conditions. First we will see the first boundary condition. This first boundary condition, consider a boundary formed by two dielectric as shown in the diagram. By referring this diagram, this line is nothing but a boundary. This line is the boundary. So below that we have dielectric material 1. Above that we have dielectric material 2. This is dielectric material 1, this is dielectric material 2. Both are combined together. That line is nothing but a boundary between first dielectric and second dielectric. We placed one box such that it encloses both the media. It covers both dielectric 2 as well as dielectric 1. The box is placed such that it covers both the media. Half is available at boundary 2, available to dielectric 2, half available in dielectric 1. Here what we are going to see, the displacement density, normal component of displacement density. This is the normal component of displacement density entering into the box, that is in the boundary, that is in the dielectric material 1. But it is leaving at dn2, normal component of displacement density vector, leaving this box at second dielectric material, right? Entering in first dielectric material, leaving in the second dielectric material, so that we will analyze whether both are equal, if there is any change in dn1 and dn2. That is our analysis, because it enter at first dielectric, leaves at second dielectric. The surface area of the box is delta S, the height is delta H, right? The height is delta H, the surface area is delta S. So at this boundary what we have, charged sheet with density sigma coulomb per meter square. So we placed one charged sheet is available. One charged sheet is placed at the boundary, sigma coulomb per meter square. So due to that we will see what will happen in this, whether both are equal or any changes is available. So this description is given. Consider a box at the boundary such that it encloses both the media. So this is the angles are given. This theta 1 is angle of incidence, entering. Theta 2 is the angle of emergence. Emergence means leaving. D1, D2 means normal component. This is the flux displacement density. dn1 means normal component, right? Now we are going to apply the Gauss law to the box. Gauss law. What is Gauss law? Normal component of flux coming out of the charged body is equal to amount of charge enclosed. Right? Flux is equal to charge, pi equal to q. Now we need to identify what is the flux available here, what is the charge available here. Then we can apply the Ampere's law. From that we can find the relation. First we will find the flux. What is the flux? What is the flux entering the box? We have dN1 is available. Normal component of flux density is entering. Then what is flux? D equal to pi by x. Displacement equal to charge per unit area. So from that we cross multiply this. Pi equal to ds. So the flux equal to displacement density into surface area. What is given D in the diagram is displacement density vector, not a displacement density vector. From displacement density vector we can find the flux using this formula, pi equal to ds. So that flux entering the box is dN1 into dx. dN1 is normal component of flux density. Flux means dN1 into ds. Similarly, what is the flux leaving the box? dN2 into ds. Right? dN1 into ds is the flux entering, dN2 into ds is the flux leaving. Then what is the charge enclosed by the box? We have sigma is available. Charged sheet sigma is placed at the boundary. What is sigma? Q divided by S. Charge per unit area. We cross multiply this so that Q equal to sigma into S. Charge equal to charge density into area. Q equal to sigma into S. So that sigma into delta S. What we have? Delta S. Right? So this is flux entering, this is flux leaving, this is the charge available. So what is the Gauss law is given by Gauss law? Net flux is equal to the charge enclosed. What is net flux? Net flux means difference between these two. dN1 minus delta S minus dN2 delta S equal to sigma into delta S. This is the net flux. Flux entering minus flux leaving equal to charge. So the delta S is commonly available. We can cancel the delta S. So dN1 equal minus dN2 equal to sigma. So what we got? This dN1 and dN2 are not equal. That is depends upon the charge. So if any charge is available at the boundary, the fluxes density vectors are not equal. It will differ. That is the relation we have. Right? So that is given here. Normal component of flux density vector is discontinuous by a amount of charge density of the sheet. Right? They are not continuous. What is the flux entering is not flux leaving. There will be some discontinuous available. Why? Due to the charge density. Suppose if the charged sheet is not present at the boundary, right? We assume that the charged sheet is available. Now, if the charged sheet is not available, what will happen? Is sigma equal to 0. So that this value is 0. So dN1 minus dN2 equal to 0. So bring the term in the right hand side so that dN1 equal to dN2. Now both are equal. Flux density vectors are equal when the charge is not available. So if the charge is not available, both are equal. So the flux line flowing from one boundary to one dielectric to another dielectric will be continuous if there is no charges are available. If any charge is available, it will be discontinuous. That is the conclusion we got. If the charge is not available, they are all equal. Right? Now it is given. The statement is given. Normal component of flux density vectors are equal. They are continuous at the boundary provided there is no charged sheet at the boundary. Right? How they become continuous? Only there is no charged sheet at the boundary. Right? From vector diagram we can write this relation d1 cos theta equal to d2 cos theta 2. From the vector diagram we can write this. Now we'll see the second boundary condition. Second boundary condition is dealing about tangential component of electric field. First boundary condition, normal component of displacement density. Now we are going with tangential component of a electric field. Right? You refer this diagram. So this is the first dielectric material. This will be second dielectric material. This line is nothing but a boundary between first dielectric and second dielectric, 1 and 2. We have one closed path, rectangular path, A, B, C, D, A, such that it encloses both the dielectric. A, B available in dielectric 2, C, D available in dielectric 1. So it covers both the dielectric. The height is delta H, length is delta L. So in this AB, what we have? ET1, tangential component of electric field intensity, ET1. In CD, ET2. See the direction, both are opposite. So this is negative. And see the vector diagram. This is tangential component. This will be normal. Electric field intensity, E1 and E2. This is angle of incidence. Theta 2 is angle of emergence. So that is given here. E1 and E2 are electric field intensity in media 1 and 2. ET1 and ET2 are the tangential component of electric field intensity in media 1 and 2. Now we need to verify whether both are equal. ET1 and ET2 are equal. Another thing, there is no charge sheet available. In first boundary condition, we placed one charge sheet. Now we are not placed any charge sheet here. Now we'll go to this. Consider a rectangular path ABCDA at the boundary such that it encloses both the media. Right. Static electric field is a conservative field. What is meant by conservative field? Net field is 0. That is integral E dot dl equal to 0. If any closed path is there, the total electric field intensity will be 0. Now we can apply this to the closed path ABCDA. We can apply this condition for ABCDA. So apply this equation to the loop ABCDA with delta H equal to 0. We assume that the delta H is approaching to 0. So integral E dot dl equal to 0 for a closed path ABCDA. So that is written in 4 parts: AB, BC, CD and DA. That is equal to 0. What is the electric field intensity in AB, BC, CD and DA? Now refer the diagram. The electric field intensity AB is ET1 into delta L. CD is ET2 into delta L. What about BC and DA? This delta H is approaching to 0. So the value is 0 here, because height is, we are approaching your height, assuming your height is 0. So we have ET1 into delta L here minus ET2 into delta L. So that is available here. As delta H is approaching to 0, second and fourth terms are tends to 0. The first term AB is ET1 into delta L. Then third term is minus ET2 into delta L, that is equal to 0. So we bring this term right hand side. So ET1 delta L equal to ET2 into delta L. This delta L got cancelled. So ET1 equal to ET2. So tangential component of electric field intensity, the first dielectric, second dielectric, both are equal. Directly we got this relation. Why? Because there is no charge sheet. We are not placed any charge sheet. So straightly we got both are equal. So that is given here. Tangential component of a electric field intensity vectors are equal. We are not having any condition. Directly we got that both are equal. From vector diagram we can write E1 sin theta 1 equal to E2 sin theta 2. E1 sin theta 1 equal to E2 sin theta 2. Similarly we got from first boundary condition also. First boundary condition D1 cos theta equal to D2 cos theta 2. Second boundary condition E1 sin theta 1 equal to E2 sin theta 2. This one displacement density, this one electric field intensity, right? For equation 2 by 1, you give E1 sin theta 1 divided by D1 cos theta 1 equal to E2 sin theta 2 divided by D2 cos theta 2. Right? So that E1 divided by D1 sin theta 1 by cos theta 1 is tan theta 1. Sin theta 2 by cos theta 2 equal to tan theta 2. now we'll substitute this. D equal to epsilon E, the relation is available. So that D1 equal to epsilon naught epsilon R1 into E1. Similarly, D2 equal to epsilon naught epsilon R2 into D2 into E2. Now we'll substitute this. E1 tan theta 1 divided by D1 is replaced by epsilon naught epsilon R1 E1. Then D2 by E2 into tan theta. This D2 is replaced by epsilon naught epsilon R2 into E2. Right. So this epsilon naught is available in both, that got cancelled. This E1 is available, that got cancelled. This epsilon R1 is available, epsilon R1 and R2. So tan theta 1 divided by epsilon R1 equal to tan theta divided by epsilon R2, right? E1 and epsilon naught 1 got cancelled. So from this relation we can write tan theta 1 divided by tan theta 2 equal to epsilon R1 by epsilon R2. So by using this relation we can find the parameter. Suppose theta 1 theta 2 epsilon R1 is known, mean you can find epsilon R2. By using three parameters, the fourth parameter can be calculated, right? So in this we discuss about dielectric boundary condition. There are two boundary conditions available. First boundary condition deals with normal component of displacement density vector. Second boundary condition tangential component of electric field intensity. Finally we got this relation also that can be used to measure the parameters. Welcome viewers, in this video we will see the magnetic boundary condition. There are two boundary conditions available, first boundary condition and second boundary condition. First we will see the first boundary condition. The boundary is nothing but two different magnetic materials are combined together. The line separating the two magnetic materials called a boundary. So now consider a magnetic boundary formed by two different magnetic material with permeability mu R1 and mu R2. So we have the two magnetic materials are combined together that form the boundary with permeability mu R1 and mu R2. When the flux lines are coming out of this boundary, its magnitude and direction changes. When the flux line flow from one magnetic material to another magnetic material, what will happen? There will be a change in magnitude and direction. So that we are going to study in this boundary condition, whether there is any change in the flux while entering into one magnetic material to another magnetic material, whether there are equal or there may be some difference is there, any deviation is there in the magnitude and angle, we are going to study in the boundary conditions. Now consider this consider this diagram. So this is the first magnetic material. 1 refers the first magnetic material with permeability mu R1. This 2 refers the second magnetic material mu R2 with permeability mu R2. Both are combined together. It is separated by this line. So this line is nothing but a boundary between first magnetic material and second magnetic material, right? So the line is nothing but a boundary. We consider one box is placed at the boundary such that it half of available in the first magnetic material, half available in the second magnetic material, right? So the surface area of this box is delta S, height of this box is delta H. What we are going to analyze? The normal component of flux density vector. This is normal component of flux density vector entering the box Bn2. Bn1 is the normal component of flux density vector leaving the box. So this flux density vector enters in the second magnetic material and leaves in the first magnetic material. So it is enter in second magnetic material, leave in the first magnetic material. So whether both are equal, we are going to analyze. Because of two different magnetic material, any deviation in the normal component of flux density vector, any deviation is there, that we are going to analyze. So this vector diagram is given. This B2. This is a normal component of flux density. This is a flux density B2 and B1. Theta 2 is the angle of incidence. Incident means entering. Theta 1 is the angle of emergence. Emergence means leaving. Right? So our aim is we need to analyze whether this Bn1 and Bn2 both are equal or there is any deviation is there, that we are going to analyze. Now we'll see the description. B1 and B2 be the flux density in media 1 and 2 respectively. Media means magnetic material. Right? B1 and B2. Theta 2 is angle of incidence. Theta 1 is the angle of emergence. Then Bn1. Bn1 and Bn2 are the normal component of flux density vector in media 1 and 2 respectively. Normal component. Now we construct a box such that it encloses both the media. That box covers both the magnetic material 1 and magnetic material 2. Now we will analyze that according to Biot-Savart's law. We will analyze based on Biot-Savart's law. Integral B dot ds equal to 0. Flux density in a closed path is equal to 0. Then what is the flux entering the box? Bn2 into delta S. Already we refer the diagram. The flux density entering the box is Bn2 into delta X. Right? So the flux. So B is nothing but pi by S. So that pi equal to B dot S. Right? So by cross multiplying this we will get. So this Bn2 is the flux density vector. Flux is nothing but flux density vector multiplied by surface area B dot ds. So that here Bn2 dot ds, because Bn2 is the entering the box. Similarly, flux leaving the box is Bn1 into delta S. Right. So according to Biot-Savart's law, what is that? The net flow of flux is 0. That is, difference between these two is 0. Bn2 delta S minus Bn1 delta S equal to 0. This delta S is common. So Bn2 minus Bn1 of delta S equal to 0. So this delta S become 0. So Bn2 minus Bn1 equal to 0. That is Bn2 equal to Bn1. What is that? Flux density entering and leaving both are equal. There is no change in the magnitude and direction. Both are equal. Why? There is no charged sheet available. If any charge is available at the boundary, that will make the deviation in magnitude and direction. But in our diagram there is no charged sheet available, so that directly we are getting these two are equal. Right? So the statement is given. Normal component of flux density vectors are equal. Otherwise, normal component of flux density vector is continuous at the boundary. Continuous means there is no deviation. Right? Now we'll go to the second boundary condition. So the second boundary condition, before going to that, we'll see the sheet current density. What is sheet current density? K equal to current per unit length. I divided by del L is nothing but the current density. So from that I equal to K into delta L. You cross multiply this, I equal to K into delta L. Right? It can be used in the derivation. Now this is the second magnetic material. These two refers the second magnetic material. This one refers the first magnetic material. Both are combined together. This line is the boundary between second magnetic material and first magnetic material. In the first boundary condition, we deals about normal component of flux density vector. In second boundary condition, we are dealing with tangential component of magnetic field intensity. Tangential component of magnetic field intensity we are going to deal in the second boundary condition. Here what we have, one closed loop is available. A, B, C, D, A. One closed loop is available. So it covers both magnetic material 1 and magnetic material 2. It covers both the magnetic material. The length is delta L. The height is delta H. The magnetic field intensity in the path AB is HT1. in CD is HT2, but see the direction, both are opposite. What about the magnetic field in the BC and DA? That is 0, because in a perpendicular path that is 0, and also the height is approaching to 0, means these two are 0. Only we have AB and CD. And our important thing, we have one infinite current sheet of charge density K is placed at the boundary. In first boundary condition we are not placed any charged sheet. Now we are placing one infinite current sheet at the boundary, right? So the description is available. HT1 and HT2 are the tangential component of magnetic field intensity in media 1 and 2, that is magnetic material 1 and 2. Construct a rectangular path ABCDA such that it encloses both the media. Now we apply the Ampere's law to the path ABCDA. We are going to apply the Ampere's law. What is Ampere's law? Integral H dot dl equal to I in a closed path ABCDA. Right? In a closed path ABCDA, integral H dot dl equal to I. Now we'll go for the further simplification. Now the ABCDA, closed path ABCDA, is now split into 4 parts: AB, BC, CD and DA. 4 different parts, that is equal to I. Now we assume that the delta H is approaching to 0. That means this BC and DA become 0. There is no term BC and DA because height is nearly equal to 0. Only we have AB and CD. What is the magnetic field intensity in AB? HT1 into delta L. We already referred in the diagram. What is the magnetic field intensity in CD? Minus HT2 into delta L, because the directions are different. Vector direction is different, so that we have got negative. That is equal to I. So HT1 delta L minus HT2 delta L, that is equal to, this I is nothing but K into delta L. Already we got that current density. So this delta L available everywhere, we can cancel. So HT1 minus HT2 equal to K. What is that? The magnetic field intensity, tangential component of magnetic field intensity are not equal. It is depends upon the current density, right? The current density of the charged sheet. In the first boundary condition, we got Bn1 equal to Bn2 directly, but here not equal. Why? That's due to the current sheet of charge density K, right? That is depends upon the K value. Suppose if the current sheet is not available, if sheet is not present, then K equal to 0. If K equal to 0 means HT1 minus HT2 equal to 0, so that HT1 equal to HT2. Now both are equal. When if it is no charged sheet is available, then only both are equal. That is given. Tangential component of magnetic field intensity vectors are equal, right? So it is very clear, the magnetic field intensity or flux density is equal only if there is no charge is available. If any charge is available in the boundary, that will affect the direction and magnitude of the either flux density or magnetic field intensity. So in this video we discuss about the boundary condition, first boundary condition and second boundary condition. Thank you.